Okay, so next topic about Grignards is things that you cannot do with Grignards. This is a really important topic because Grignards happen to be very strong bases and very strong nucleophiles, so they react with all sorts of functional groups, and you can end up with lots of side reactions if you're not careful about when you use them. So let's list a couple things that you cannot do with Grignards. And we've already talked about a few of these, but just to remind you, one thing you cannot do with a Grignard reagent, and this is our abbreviation for a Grignard reagent, is that you cannot do SN2 reactions with them. Grignard reagents will not do SN2 reactions. On paper, it seems like a reasonable idea. So for example, if you have something that's a perfect SN2 substrate, you might think, well, a Grignard reagent is a good nucleophile. So maybe I'll take some methyl magnesium bromide and have that attack that partial plus carbon and do an SN2 reaction. And it just doesn't happen. This would give no reaction. So Grignards are good nucleophiles for attacking carbonyls, but not for doing SN2 reactions. Just something to keep in mind about them. The second thing is that water will destroy a Grignard. Water will the Grignard that you formed by putting in magnesium, it'll get ruined if you have water present. So most of the time you want to be very careful not to add water to a reaction until it's all done and you're ready to quench the reaction. But there are times when this might actually be useful. So we'll add here that although this is a useful reaction, if you actually want to change a bromide or a chloride or an iodide to a hydrogen. So occasionally that's something you might want to do. For example, let's say you have cyclopentane and you have a bromine on here, and you actually, at the end of a synthesis, you don't want that bromine there. One little trick to get rid of it is you could add magnesium. That turns this into a Grignard reagent. And then normally we don't want water present, but if we do add water, this Grignard reagent, besides being a good nucleophile, it's a great base, and it's just going to grab a proton off of water. And the net result is that our bromine, that was originally on the molecule, is replaced with a hydrogen. And sometimes this trick is used occasionally if we want to deuterate a compound. We could use deuterium oxide here, D2O. And then instead of a hydrogen going on the molecule, it would be a deuterium. So that's a little trick to deuterate certain spots of molecules. Okay, a big important thing about Grignards is this fact that they're really strong bases and really strong nucleophiles. And so really strong bases will deprotonate acidic protons. So you basically cannot use a Grignard reagent in the presence of anything that's even slightly acidic. So this is number 3 on our list, is that Grignards will deprotonate acidic protons. So what does that mean? Do not use them in the presence of, and now I'm going to draw a whole bunch of different functional groups that you cannot use or that you cannot have present when you want to make a Grignard reagent. Okay, so a carboxylic acid, that has an acidic proton that will get pulled off by a Grignard reagent. An alcohol has an acidic enough proton that a Grignard reagent will deprotonate it. Amines, if they have a hydrogen on them, can get deprotonated by a Grignard reagent. Thiols, so an SH group, that proton is acidic. And terminal acetylenes, we learned that this is a very slightly acidic proton, but a Grignard reagent is a strong enough base to deprotonate that. So these are all different groups you cannot have present when you form a Grignard. So for example, let's say that you want to make a Grignard reagent out of this molecule, but it has an alcohol on it. As soon as you add the magnesium to try and form the Grignard, let's see, we'll draw this as the Grignard reagent. As soon as you form that Grignard reagent, there are a whole bunch of other molecules floating around that are also alcohols. And so this is just going to pull a proton off of any one of those. So this will grab a proton off of here, and then it'll kill this Grignard. That won't work as a Grignard anymore. And so whatever reaction you're trying to do just won't work. Another example where a Grignard reaction wouldn't work in the presence of one of these functional groups. I'm going to erase this so I have more room. So a second example of this kind of situation is, let's say that you have a Grignard reagent. Okay, so let's say you successfully make this Grignard reagent, propyl magnesium bromide, and then you want to react it with, let's say it's a ketone. If you happen to have something acidic on the same molecule, like say there's a carboxylic acid there, you want your Grignard reagent to react with the ketone. Maybe that's your plan in the synthesis. But what's actually going to happen is that it's not going to attack the ketone. It's going to pull off that acidic proton off of the carboxylic acid. And so what you're going to end up getting is not the reaction that you want. So those are a couple examples of cases where you need to make sure that you don't have an acidic proton present on some other part of the molecule when you make a Grignard reagent. The fourth thing in my list is something that will actually come up in the next chapter when we talk about epoxides, but it's worth mentioning now, is that Grignards react with epoxides. And epoxides, remember, those are those little three-membered rings with an oxygen in them. So a Grignard reagent is a great nucleophile. We've seen nucleophiles, we've seen water as a nucleophile open an epoxide. So a stronger nucleophile like a Grignard reagent is for sure going to open an epoxide. It's going to attack one of those carbons and pop open the ring. And the net result here is something that looks like that. But if you don't want your Grignard to react with the epoxide, then you can't have the epoxide present when you make your Grignard. So let's say don't use Grignards when epoxides are present. Unless you're really trying to do a reaction where a Grignard reacts with an epoxide. Okay, so those are some rules about when you are not supposed to use Grignard reagents, and this would be a good time to try number 4 on the worksheet. So pause your screen, take a couple minutes to go through. There are a whole bunch of different scenarios here, letters A through G, and you're supposed to decide if that reaction would work as written, and if not, then explain why it would not work. Okay, so while you do that, I'm going to erase my board and get ready to go over these. Okay, so letter A. It looks like we have an alkene present when we form a Grignard reagent. So when I add the magnesium, this is going to become magnesium bromide. And an alkene doesn't do anything to interfere with a Grignard reaction. It's a great functional group to have present when you're doing a Grignard reaction, because you can later turn it into something that's more sensitive, that might react with a Grignard. In the second step of this reaction, it looks like we're just adding a ketone here. We're doing this as one step and water as the second step. So this should work exactly as written. This is going to form the product that it shows there. So this one we would say works. Okay, letter B. Letter B shows a bromide. And rather than writing this out as separate steps, everything is smushed together. Magnesium, water, and the aldehyde are all written together as if they're all thrown into the beaker at once. And so this would not work because you have water present when you're trying to form the Grignard reagent. So this one will not work as written. Letter C. Now we have a ketone attached to a chloride, and in the first step, magnesium is added to form the Grignard reagent. So the magnesium is going to insert here next to the chloride, forming a Grignard reagent. And then it looks like in the next step what we want to do is to add this Grignard reagent to this aldehyde to form the product shown. But the problem is that the original Grignard reagent has its own carbonyl compound in it. And so it's just going to react with another one of these compounds. Maybe this is a chloride or maybe it's turned into a Grignard reagent. Doesn't really matter. This is going to do a side reaction where it attacks this ketone rather than attacking the compound that you want it to react with. So you're going to get all sorts of side products here. So this reaction won't work. Okay, letter D. Let's make some room on our board. Letter D, now we have a ketone and an alcohol on the same molecule. And it says we're adding 1 equivalent of phenylmagnesium bromide and then quenching the reaction with water. And the idea is that we want to have the Grignard reagent attack this alpha carbon and eventually form an alcohol there. But the problem is that we have an acidic proton right here. So our Grignard reagent, instead of doing what we want it to do, it's going to come over here and it's going to pull off this acidic proton. And since we only have 1 equivalent of Grignard in there, that's basically going to kill all of our Grignard reagent. So this reaction won't work as written because you have an acidic proton present when you're trying to form your Grignard reaction, or when you're trying to run your Grignard reaction. Okay, letter E. We start out with an aldehyde, and we have a bromide, and I'm going to just write in the results of the first step. You're going to add magnesium and make your Grignard reagent. So this is starting out, it looks a lot like letter C, but the difference is, if we look at the product that's being formed, it's actually a ring. And so if we think about what this Grignard reagent is going to do if it reacts with itself, we have 1, 2, 3, 4, 5, 6 carbons. If you go from the nucleophilic carbon to the electrophilic carbon, you can make a 6-membered ring. And this will kick up and then eventually get protonated to become an alcohol. So we actually do form this molecule here. So this reaction works as written because the intention was for the Grignard to react with itself. Okay, letter F. We have a carboxylic acid. We're putting in 2 equivalents of a Grignard reagent, phenylmagnesium bromide. And then we're quenching this with water. Okay, so if we think carefully about what's going to happen, the first equivalent of the Grignard reagent is going to act like a strong base, and it's going to deprotonate the carboxylic acid because we have this acidic proton here. So that's what the first equivalent does. And then the second equivalent might actually come in and attack here. And so you could get something like this. O dot dot minus, O dot dot minus. And you'll actually learn the mechanism for this next semester. But when you quench this with water, you're going to end up forming a ketone. You are not going to get the product that's shown. You're not going to get the alcohol. The problem basically is that the phenyl can't add twice because the first equivalent of Grignard gets quenched by that acidic proton. So this one won't work as written. And that was letter F. And the last one on the worksheet, letter G. This one has an epoxide present. And we just talked about how Grignard reagents react with epoxides. So this one, without going into too much details about it, we're putting in 2 equivalents of Grignard. But the reaction, I'm just double checking what's going to happen here. CH3, MgBr. One of the things this Grignard reagent is going to do is it's going to come around here and attack the epoxide and open it up. So at the end of the reaction, you will not have an epoxide present. So without thinking too much about what else happens, this one will not work because of the epoxide present. Okay, so that was a good lesson in what not to do with a Grignard reagent.